All right. So conduction means conduction in semiconductor after we dope the pure semiconductor. So this intrinsic semiconductor will become a semiconductor that can conduct current. Okay. For example, when you have pure semiconductor silicon and you dope with N-type semiconductor, and this extrinsic semiconductor will become N-type extrinsic semiconductor where it can conduct current. Okay, that is why we learn electronic circuit. Okay, we want to make the circuit to conduct current where electron can flows and you can measure the current. Okay. All right. Next, why do you have to learn the electronics? Because look at your surrounding now. Okay, you are fulfilled with the electronics gadgets, your phone, your laptop, your computer, everything, electronics. Okay, electronics gadget. Okay, so many state-of-the-art technologies are interdisciplinary. Okay, for example, your television at home, your LED. So television use LED. So LED is electronic device where it is a diode initially, and then semiconductor material. So automotive in car where you have sensors in car, that is the electronic part in your car. Okay, automotive not only in mechanical itself, it is combined with the electronics. So everything surrounds you are electronics. Biosensor, so medical staff are using electronic. When we talk about sensor is electronics part, okay, electronic devices. So it involved with interdisciplinary. Okay. All right. So these are the examples. Okay. So this is the diode. Okay. When I said diode, so diode is actually the device that has, so if you still remember, so this is the symbol of a diode. Okay. So diode is made up of p-type and n-type. If you still remember, do you remember? So when we talk about diode, it is a electronic device that combine between p-type and n-type semiconductor. So when we talk about diode, we will talk about, if you see your course outline, you have the p-n junction. Okay, p-n junction. So why does p-n junction is so important? Because what is the junction? So it is actually in between this. So what happened at this junction? Okay, so in order to make this diode turn on, okay, we need a junction with a small gap. Okay, small gap. Okay, if you have a junction with a small gap, okay, then electron can pass through, okay, from p type to n type. Then only this diode can uh, turn on. Okay, forward bias. Okay, it will be forward bias and current can flow. Okay, so this diode will turn on and current can pass through the PN junction because of this PN junction is small. Okay, so small as in it is almost overlap. Okay, it is almost overlap where there is no gap, almost no gap in this junction. Okay, what about if this PN junction has wider gap? Okay, wider. So when we talk about wide, so maybe you have like this wide. So when you have this wide, this electron, okay, this electron cannot pass through. Okay, electron cannot pass through this PN junction. Therefore, this diode will be reverse bias and this will be turned off. Okay, and you cannot measure current. Current will be zero here. Okay, so now you will hold the concept, okay, of forward bias diode and reverse bias diode. Okay, when diode in forward bias, then you can measure the current. There will be a current flow. Okay, there will be a current flow. But when when the diode is reverse bias, means the junction is large, okay, wider junction, and it will be off. Okay, reverse bias means the diode off and current cannot flow because electron cannot pass through the gap. Okay, so this is the gap. Okay, this is the gap, the junction. Electron cannot pass through the gap, therefore no current. Okay, I just want to give a recall here. Okay, so you know about okay, later I'll show you. All right, so let's okay, so so this is a very simple one, diode, and then inductor, and then you have capacitor, okay, as a storage element, as a charge storage element. You have learned in the electrical circuit analysis, okay, a resistor as well as transistor. So you have BJT, bipolar junction transistor, and this is MOSFET, okay, MOSFET, okay, and then the build up of these electronic devices, diode, inductor, capacitor, resistor, transistor, you were made up an integrated circuit. Okay, so this IC is actually the combination of all these elements, okay, electronic devices. Okay, so you will made up an integrated circuit. So in your electronic device, in the electronic gadget now, okay, you actually, in your computer processor, you actually using this integrated circuit IC. Okay, so why you have to learn this? Because you need to know what is inside this IC. So inside the IC, you have these particular electronic devices. All right, so electrical devices where the charger, okay, the charger of your phone, that is electrical part. So the mantle, the mantle lamp is electrical charges. The fan is electrical charges. Okay. Okay, what is electronic? It is the branch of physics that deals with emission of an effect of electron. Okay, electrons. We're gonna listen to a lot of electrons today, electron motion, electron charges, and so on. All right, so electronic devices is electronic building block, okay, in discrete form with two or more connecting leads, okay, or metal pads, okay. So components are connected together to create electronic circuit with a particular function, such as amplifier, radio receiver, and oscillator. And active components are sometimes called devices. Okay, semiconductor material. Okay, semiconductor material. The one that I think you all know now is silicon. Okay, silicon and germanium. Okay, so semiconductor. If you still remember, okay, if you still remember the periodic table. Okay, periodic table. Okay, where you have from group 8, okay, to group where you have from group 1 to group 8. So silicon and germanium is in group 4. Okay, so silicon and germanium from group 4. So group 1 is a material that is conductor. Okay, group 4 is material of semiconductor. Semiconductor means, okay, semiconductor means it could be either a good conductor or good insulator. Okay, so this is conductor from group 1. Okay, if you still remember, from group 1 until group 3 is conductor. Okay, and then you go through group 1, 2, 3, 4 is semiconductor, 5, 6, 7, and 8. Okay, 7 and 8 is actually insulator. Okay, insulator. Okay, so semiconductor is in between conductor and insulator. When I write S/C is semiconductor. So this semiconductor could be a good conductor or a good insulator. How we want to turn this semiconductor into conductor or into insulator, we have to do a doping process. Okay, a doping process. Now at initial state, this is intrinsic semiconductor. Okay, after we do a doping process, we gonna have an extrinsic semiconductor. That extrinsic semiconductor could be conductor or insulator. All right, so what is conductor? So when I say the conductor, do you have any idea what is conductor means? Hello, guys, are you still there?
Yes, doctor, we are here.
All right, so what is conductor?
Something can
You
conduct
want example or
electric
what?
current easy.
The example,
Conduct electric.
yeah,
Example,
yeah, yeah. Example is some things like carbon, where your pencil lead, you have carbon, the black one, right? Or metal. So that is conductor, where it can conduct current. So in the electrical part, electricity, I know that in your electrical circuit analysis, you learn about electrical part. Okay, you do when you want to connect between, for example, between resistor to capacitor, so on, you need a wire. So wire is one of the stuff that conductor. Okay, insulator is something like wood. Okay, where you insulate the current. No current cannot flow through it. Okay, like rubber tapper. So that is the example of insulator. Semiconductor is in between it. So in between conductor and insulator. Okay, so it could be neither good conductor or insulator by what? By using doping process. Okay. Later, I'll show you what is doping process. Okay, so conductor, a material that allows electrical current to flow through easily. Okay, it has valence shell. Okay, once valence shell. Okay, if you still remember, so this is the example for copper. So this is coming from the group 1 from the periodic table. That's why it has one valence electron. Okay, for insulator, is actually the outer shell is perfect. Okay, it's perfect. It has 8 valence shells. So this is the for example, neon. Okay, neon from group 8. Okay. All right, semiconductor, a material that has value of electrical resistance between conductor and insulator. It has 4 valence shell. See, 4. So we want to make it complete. Okay, so that's why we have to dope this with other material so that this valence shell will become complete. So to what material we dope is defined whether it will become conductor or insulator. Okay, so so this is your silicon. Okay, so this is your silicon. So this is your valence shell. Okay, so electron at valence shell, we call it as a valence electron. Okay, so when we talk about valence electron, okay, you need to know the energy. Okay, the energy band. Okay, so you have an atom. Okay, you have an atom. So in the middle of your atom, you have nucleus and proton. Okay, these are electron. So electron is located at this orbital shell, at its orbital. Okay, for example here, this electron, the okay, I think the nearest to nucleus has 2, and then the rest it has 4. Okay, so why does this electron has less energy than this electron more energy? Why does this electron that which is near to nucleus has less energy, and why this electron far from nucleus has more energy? Who has the idea?
Can you read, Doctor, please?
So so this electron in the second shell has less energy compared to this electron in the outer shell has more energy. What does it mean? So this is quite a famous question. Maybe in the quiz or test. Okay. I
Maybe,
have
Doctor, it is more in insulator than conductor.
no. So we are talking
Is it
about one
because,
silicon. Yes. Is it because?
Doctor, is it because the outer shell electrons have the more tendency to go outside of the atom?
Yes, correct. Nashra. All right. Nashra Tasnim.
Yes, Doctor.
Yeah. So this is because, so Nashra got the idea there. Okay, so it has so this valence electron in the valence shell has tendency to actually pass through this shell and become outer electron. Okay, so because of this, okay, let's we go back to nucleus. So nucleus is actually has energy. Okay, it has energy. Okay, it has energy to attract all these electrons to stay at their shell, at their orbital. Okay, so since this electron at shell 1 very near to this nucleus, so the attraction is strong. So this electron needs less energy to stay in that shell 1. So it is like so relaxing. I don't need a lot of energy to stay in this shell 1 because I have a lot of attraction energy from the nucleus because it is very near. However, for this electron in shell 2, okay, in shell 2, it needs more energy because the attraction here is become weaker. Okay, it is still attracted because nucleus has a lot of energy, okay, to attract this electron, but then it has less. Okay, so the attraction is less. Therefore, this electron need more work. Okay, need more energy to stay here and not to going out somewhere. Okay, so this is the explanation. You can listen again to my lecture or you can read the textbook later. Okay, all right. Okay, so the energy band. Okay, so the energy band. So when we talk about this is the nucleus and then this is the valence shell. So valence electron here, we call it electrons at valence shell, we call as a valence electron. So at this different shell has different energy. Okay, so now, okay, let's take a look here. So this is your nucleus. So the only important things that you need to know is the valence band and the conduction band. So in between the valence valence band, okay, it is actually some layer where we call this a first band, second band, and so on. So what is important here is the valence band. Okay, so this pink color here is a valence electron at valence band. Okay, now we are talking about at okay, at t equal to 0, where all these valence electron are stay there. It's like sleeping here. Nothing can change this valence electron because they're going to stay here forever until we give energy. Okay, energy in terms of temperature. Now the temperature is 0 Kelvin. So everyone is sleeping here. So electron is stay, valence electron stick in the valence band and no excitement here. So this is in the form of unexcited. Okay, unexcited. Okay, so what happened next is I'll tell you next. So valence band is the highest energy level that valence electron can attain. Okay, and then conduction band is the most energy level of an atom, and unfilled band. And forbidden gap is somewhere there we couldn't see it here, but it is forbidden for the electron and hole to be there. All right. Okay, so now is you imagine at T equal to 0 Kelvin, and this we call it unexcited. Okay, later I'll explain what happened when the temperature increase. Okay, when the temperature increase. All right, so this is the difference of energy gap. Okay, so where is energy gap is here. So this is the energy gap. Okay, so when we talk about, sorry. So this is energy gap. Okay. Okay. So this is energy gap. So for conductor, it has almost overlap energy gap. Almost overlap. For semiconductor, in between insulator and conductor, and for insulator has the largest energy gap. Okay. So energy gap is when electron acquires sufficient additional energy. Okay, it can leave the valence shell to become free electron. Okay, so energy gap is the difference between valence bands and conduction band. Energy gap, the amount of energy that valence electron must jump, okay, from valence band to conduction band. And once the conduction band, the electron is free to move throughout the material. All right, let's go back here. All right, let's go back here. Okay, now, so this is unexcited, okay, unexcited, okay. So you have energy gap. So this energy gap is actually depends on the type of material. So the value here depends on the type of material. If it is silicon, it could be 0.7 volt. If it is germanium, it could be 0.3 volt, depends, okay. Now, just now I talk about 0 Kelvin, where unexcited means that all these valence electrons stay at their position at the valence shell. Okay, what happens if we increase the temperature? Okay, means we give energy to this valence electron. Okay, energy is in a form of heat. Okay, what happens if we give heat to uh, this? Okay, heat means at high temperature. So this valence electron here will become excited. Okay, so this valence shell will become excited. Okay, so this valence shell, when it got heated and it means it get energy. Okay, means it get energy and it will if it get energy and it can pass through this energy gap. Okay, so this will jump to the conduction band. Okay, will jump to the conduction band and it will leave a hole here, hole. And this electron just now jump here will become electron here. So this electron, we call it as a conduction electron, or some would use free electron. Okay, so not talking about only one electron jump. So all valence electron here will jump, become the conduction electron or free electron. So conduction electron and free electron are the same, but the terms or only the name are different, but it's actually the same. Okay, conduction electron and free electron. So as you can see here, so these free electrons here are actually moving at the conduction band. So where does the idea of current flowing into the diode? So it is actually the movement of this free electron. When valence electron has sufficient energy to jump through this energy gap, to pass this energy gap and become conduction electron. So this conduction electron movement, okay, this is moving around, is actually producing a current. Okay, remember that. Okay, since you are electronic student, no matter what electronic student or mechanical student, so where does current come from? When people ask you, it is actually the movement of conduction electron or the movement of free electron. When there is a free electron exists and this free electron move around and it will conduct current, then you can measure your current of the diode or anything, BJT, whatever. Okay, so this is the concept. So this is the concept all about. But I'm not finished yet. Why? Because what happened when we take out this heat? Okay, so we take out this heat. Okay, no longer heat. So what happened to this? So it may occur that these free electron tend to go back to its holes. Okay, it tend to go back to its holes, and this process, okay, this process we call it as a recombination process. Recombination process. Okay, so this pair, hole and electron, this pair we call it as an electron hole pair. So this is the process of how electron, okay, get excited, okay, from unexcited at 0 Kelvin to excited at when we increase the temperature. Right, so there is a question here. So doctor, after electron jump to conduction band, will be any electron in the valence band? Okay, so in the valence band, only left with holes. Okay, hole. So this is hole. The circle one with empty things, that is hole. So only hole is in the valence band. Okay, so this electron, okay, this electron will pass through here. Sorry, where is my mouse? So this electron jump to the conduction band and it will leave a hole. So only hole exists in the valence band. Okay, all right. Okay, this one done this. All right. So I hope you understand the process just now. Okay, so the insulator have no free electron. It has wide energy gap. Okay, it has wide energy gap. So therefore, it's very difficult. Okay, since it has wide energy gap. Okay, for example here, so this is the conduction band, so this is valence band, so this valence electron very hard to jump, so cannot jump to the conduction band. Therefore, because this energy gap is very, very large. Okay, so therefore, no free electrons here. Okay, no free electrons here. And when there is no free electron movement and current here is 0. Okay, no free electron and current 0. That's why it becomes insulator. Insulate, cannot conduct current. Okay, all right. Okay, so for semiconductor, so it has no free electron. Okay, has a much narrower energy gap compared to the insulator. Okay, and however, the gap permits some conduction with the application of moderate force. Okay, in semiconductor, it has 4. Okay, it has 4. 1, 2, 3, 4 for germanium. For silicon, it has 4. So how we want to complete this 4 become 8? So we need a doping process. Okay, a dope. Okay, later I'll show you. So conductor. So a particular valence electron with free to move. All right. So example, a conductor. There's many from group 1 to group 3 semiconductor. Conductor. Lithium, natrium, gallium, copper, argentum, aurum. Okay, the energy gap is almost overlap or very, very small. So very easy for the valence electron to pass through the energy gap and become free electron. Therefore, it produces a lot of free electrons. Okay, here. So for example, let me show you here. So you have the conduction band and you have your valence band. So the energy gap is very, very small. So from electron here, we can see that all the valence electron can pass through, become free electron. Therefore, many free electrons are moving around in conductor and it will produce a very high current. Because of free electrons, a lot of free electron, therefore current is also high. And it can conduct current. Right. So next, conduction in semiconductor. So up to now, do you have any, if let's say a quiz or a test asks you a question, how current is produced in semiconductor? Do you have the idea how to answer this?
With the doping operation, doctor, from
Yeah.
from moving from the valence band to the conduction band
Yeah.
of the electronics.
Yes, you have to give the story like that. I mean, the movement of the valence electron get heated and then jump through the energy gap, get sufficient energy and pass through the energy gap and jump to the conduction band and become a free electron. So the movement of free electron here is actually produce current in semiconductor. So that's how the story goes. Okay. I hope you get the idea. I believe that you get the idea, right? Okay. So in
Yes, doctor, thank you.
all right, great. Okay, so in semiconductor, current is produced in 2 different ways. Okay, there are electron current and there are electron current. Okay, I go back a little bit here. Okay. I need to explain this, although this is quite advanced, but it's okay. So for your knowledge, okay. So so like I said just now, so this valence electron get energy, okay, from the heat here. So it is able to pass through this energy gap and jump to the conduction band. It become free electrons. So this free electrons movement moving around here, okay, is actually produce a current. So this current, we call it as a electron current because it made up from the movement of free electron. Okay. However, let's take a look at a very rare case here. Okay. So when it leave, when this valence electron jump to the conduction band and become free electron, it will leave a hole, right? We will leave a hole. So this hole is actually has also tendency to move around, but very, very slow, very like so super slow. Okay. And this slow movement of hole also produce a current where we call it as a hole current. Sometime and most of the time, hole current will be neglected because sometimes the value is maybe 10 to power 20 pico, 10 to power of 12, minus 12, where we can ignore this current. Okay, so when we talk about low level, we know the current is produced by electron current. Okay, the movement of electrons. So that is electron current. So it's a little bit advanced. I'm giving you the idea that the hole is also moving around, but very, very slow when there is a movement of carrier of holes or electrons. So in hole also moving around, very slow, and it has tendency to produce current, which is very, very small current. Okay, sometimes neglected. Okay, let's go back to the slide. Okay. Okay, so I hope this answers everything just now. So it's just a simple question that maybe carry you about 5 marks. So I hope you know how to answer it. Okay, conduction versus temperature. Why is it temperature very important? Because just now to give energy to the unexcited atom silicon just now, we give heat. Okay, heat in the terms of temperature. I believe that you all know. Unexcited just now temperature at 0 Kelvin. But when we give heat at high temperature, so we put the silicon or silicon unexcited atom in at high temperature. Okay. So at high temperature, so 0 Kelvin means no thermal energy. So it's like everyone is sleeping in their shell. Valence electrons sleep in their valence shells and nobody moving around. Okay. So when temperature is raised, okay, when temperature increase, okay, so it has tendency to break the covalent bond where the valence electron has energy to sufficient energy to pass through the energy gap and become valence electron. And even at room temperature also, we might say at high energy. Okay. So for the at room temperature, many electrons are set free, set free, become free electron or conduction electron from their covalent bond from thermal organ or ionization. Okay. So when more valence electrons jump to the conduction band, so the semiconductor material conductivity increases and become free electrons. Okay, so then don't get confused. Sometimes they also use as terms conduction electron. When I put E slash above like that, not my name, Izaila, is actually electron. Okay. Up to now, I hope that you have
Okay, Doctor.
memorized my name. I hope up to now you have memorized my name. You can call me Dr. Izaila. Okay. All right. Conductivity in semiconductor is directly proportional to the temperature. Why we said so? Because the higher, okay, so this is your valence band. VB is valence band, not volleyball. Okay, CB is conduction band. Okay, so when it is being heated, temperature. Okay, so this will become energetic, okay, to pass through this energy gap. Okay, what happened? Can you imagine what happened when we increase the temperature? So more of valence electron. Okay, now we are looking only one silicon atom. It's actually crystalline. So we have a lot of silicon crystalline. Okay, so there are many of valence electron will pass through this energy gap. Okay, here is just a drawing for, so maybe you have thousands valence electron pass through this energy gap and become free electron. Therefore, this statement said conductivity in semiconductor is directly proportional to the temperature. Means if you increase more temperature, there is more tendency of valence electron to pass through this energy gap and become a lot of free electrons. Okay, now it's only four, but it's actually you have a lot. Okay, you couldn't imagine it. Okay, you have maybe millions of valence electron pass through this energy gap and become free electron, and it will conduct current. And when there is more free electrons developed, therefore more current can be produced. Okay, that's why it is proportional to the temperature. Okay, so this in a better diagram. Okay, just now I have drawn this just now. Okay, but this one is better than my drawing. But I hope from my explanation just now you understood. Okay, you understand what I've explained. So this is actually the same thing what I have explained just now. Okay. You have valence band, you have conduction band, and this is your energy gap. Been talking a lot about this, right, today? Okay, so it is being heat up at high temperature. So this is how it goes. Okay, it will leave a hole and become free electrons, and then this free electron movement is actually produce current. Okay. Okay, so this is the story how it goes. Okay, from unexcited to excited. Okay, the process is the process where the electron go back to the hole when we take out the heat is recombination process. So the pair between these two is actually electron hole pair. So you can read it again or you can watch the video again. Okay, so free electron and holes as a charge carriers. Okay, like I said just now, charge carrier is free electron. Okay, hole also charge carrier. Okay, so it can make electron current or hole current. Okay, so just now you see only one. Okay, only one. Okay, I always want to explain it in a better way. Okay, so now you see only one silicon atom. So one actually surrounds you, means the in real one, it is actually not only one. Okay, not only one atom, it is a millions of atom, so millions of silicon bond together. Okay, when it is bond together, it is actually looks like this. Okay, this we call it as a crystalline, silicon crystalline. If you ever heard, the researcher found out looking at the microscope, silicon atom is actually look like crystal. So the coordinate very cleave and being coordinated each of the atom. So it is look like this. So silicon, silicon, silicon. See, it is bond to each other to complete it. Okay, if we look at this example. Okay, so this silicon has complete. So it share with this silicon. So this one share with this silicon. This one share with this silicon. Okay, so it tends. So when we put at high temperature, this valence electron tend to jump through. Okay, the conduction band and become free electron. So the pink color one, this one is actually free electron, where the free electron moving around and you can produce the current. Okay, so when it become free electron, it produce electron current. So the hole just now I said, so it is very slow movement, but it can produce current. We call it as a hole current, but in a very, very small value lah. Sometimes like picoampere, nanoampere, where we can ignore it. Okay. So this is how it looks like. So the movement of electron. So the movement of electron is in from left to the right. Okay, so when you measure current, current is actually opposite direction of the movement of electron. Okay, when you measure current, so current is opposite direction of the movement free electron. Remember that. Okay, remember that forever until your final year, until you're working and forever. Okay, so whole current is the movement of whole. Okay, so but very, very slow. Okay, so right. Let me see the time now. What is the time now? Oh, 12. Okay, do you want to have a 5-minute break? Hello?
Yes, doctor, I think it will be good.
All right, okay, so let's have 5-minute break before we proceed. Okay, you can have a cup of coffee, or you maybe can have, you can go to the kitchen or whatever you want to do, and we come back after 5 minutes. Okay?
Hello, excuse me, ma'am.
Yes, yes, yes.
I have a matter regard my registration.
Mm-hmm.
So,
Mm-hmm.
so I'm 2018 intake student who actually missed this course, but I'm currently taking it.
Uh-huh.
And as you know, the code has changed based on these
Yeah,
2
yeah,
years,
yeah.
right?
Yes,
So yeah,
correct.
all my academic achievement will be based on the old code, but the registration is based on the new code. So
Oh,
yeah,
let me see. Have you registered IMSS yet?
yeah,
I mean,
I have already registered. But the thing
you're
is,
in section what?
6.
6. Okay, okay. Oh, yeah. So your code is SKEE1073, right?
Yeah.
Uh-huh.
So in order to have my academic achievement in the right path, I need to change the code in the academic office.
Oh, really?
Yeah.
Oh, I also don't know about this. What's your name?
It's Mokman Ali.
Not in the list yet, but not in my list yet. I cannot see your. Yeah, I can see your name. Okay. All right. Oh, so you need to change, right? You need
Yeah.
to change the code. I see. Okay. So do office will do it for you?
Yeah, all I need is
Mm.
your signature, but I'm not sure if my
You can.
attendance, my tests will be based on old code also or new code. That's
Okay.
Brother Mu'min,
yeah.
doctor, I have the same issues, me and Abdurrahman Ali. We both, and Mu'min, we are still in the A18KE. So our code is SKEE1073.
Oh.
That's a link. You register in it, you fill the form, and you inform the office. I just did, doctor wanted to inform you that we are in the old code.
I see. Okay. Abdul Rahman and Muhammad Monter, right?
Yes, Muhammad Manzar and Abdurrahman Ali, and as I saw, Mu'min Ali.
I see. Okay. I noted that. I think once they convert the code, will be okay.
Yeah, it will be okay, but
Uh,
as for now, I just need your signature, I guess, on the form.
uh, Maybe you can PM me private in the Telegram, send me the form, so I'll give you the digital signature.
All right, sure thing.
All right. Okay.
Okay, thank you, ma'am.
All right. So previously you took with who? This subject?
No, I didn't
No?
take it. The first
I
time.
didn't take it.
Yeah.
First time. All of you first time.
No, doctor, this is my second time because I took it on the first. I took the first test, then I dropped it.
Uh-huh.
And Abdurrahman Ali, he failed in the subject, as I know.
Okay. So with whom you took?
I took it with Dr. Prosper.
I see. Muhammad Ali? Dr. Puspa as well.
I don't know.
Okay. All right. Okay. Okay. No problem.
So basically, we are third year students still taking first year studies.
Yeah. Seniors taking this. That's good. You have learned a lot.
Yeah, basically, it's key. E student don't need the subject much, but yeah, through our labs and understanding, we knew about diodes and stuff.
Yeah, but this is the beginning of the semester. So after this, you will learn to analyze the DC and AC circuit. So in electrical circuit, you didn't do that until AC. So here we do until AC. At least you have the idea how to analyze AC circuit.
Yeah, true.
Okay. All right. We passed 5 minutes. Yeah, done, right? Oh, I need to drink a bit. So in your country, what time now?
Well, for me, I'm still in Malaysia. I didn't travel.
Oh, okay. The Abrahman just now? What? Anybody in overseas right now? What time? So or
Yes,
all of you?
doctor.
Uh-huh.
Doctor, I'm in Bangladesh and it's
Uh-huh.
10:15 a.m. in my country.
Okay. Just nice. I mean, not early morning because before your class, I have master's class. So master's class, they're from all foreigners all over the world. So there are 2 a.m., 3 a.m. They have to listen to lecture. So poor them. But that's okay. All right. So let's continue the lecture. Okay, are you ready?
Yes.
Okay. Ready or not ready?
Yes,
Have
doctor.
to. All right. Okay. Great. So next, what is intrinsic, extrinsic, doping, n-type, don't accept, blah blah blah. Okay. So revision. So this is since this is a continuous class. So this actually for last time where we have 1 hour class, and then the next class I do a little bit revision. So I think it's fresh. No need to do revision. Okay, so for the revision current also you can read on your own. Okay, later I already post the slide. Okay, intrinsic semiconductor. It is a pure semiconductor. Silicon, germanium, electron and hole concentration are relatively small, hence very small current are possible. So poor conductor because the total of number charge carrier are small. Okay, it could be semiconductor do not conduct current well in their intrinsic state. Okay, so intrinsic semiconductor contains very few free electrons. There are, but very few, very less. Okay, so pure semiconductor crystal are very poor conductor. Okay, at high temperature, we can make this semiconductor become conductor. Okay, so because of the thermal carriers, because of the high temperature, we produce a lot of free electrons, and because of this thermal carrier, the current is flowing. Okay, however, there is a better way to its conductivity. Okay, what is the better way is, like I said just now, adding impurities to pure semiconductor and become extrinsic semiconductor. All right. So how to make this? Okay. So you have a pure semiconductor, the one that I have explained just now. Pure semiconductor is silicon. Okay, is silicon. All right. So we add this pure silicon with impurities. Okay, and it will become semiconductor. But there is a way to add pure semiconductor, pure silicon with impurities. So the way is doping process. Okay, doping. Okay, so what is doping? So doping, why we do doping? So one of the major reason we do doping process is to increase the conductivity of that semiconductor material. Okay, where we can produce a lot of extra free electrons and also extra free holes. Okay, so this is the doping. Okay, doping is done to increase the conductivity of the semiconducting devices, where it creates an extra hole or provides an extra electron depending on dopant. What type of dopant we dope? Okay, so extrinsic semiconductor. So also known as a doped semiconductor. Okay, electron and hole concentration can be greatly increased by adding control amounts of certain impurities to intrinsic, and this is we call is a doping. Two types, N-type and P-type. Right, doping has two, N-type and P-type. So the other name for N-type is pentavalent. The other name for P-type is trivalent. Okay, all right. So for N-type, okay, if you have silicon, okay, you dope with who know how to pronounce this SB? What is SB? I forgot. Plumbum? No. Okay, whatever. We dope with this SB. So SB is N-type. Okay, N-type where we known as a donor atom. So when we dope with donor atom, as you can see, there is an excess atom here. Okay, one excess atom. So N-type is the major when now not only one excess atom. So when we talk about a lot of atoms, so this is one block. So we maybe have 1,000 blocks. So a lot of donor atom will be produced. So the majority carrier in N-type is electron. Okay, electron. All right. So this a donor electron, okay, this donor electron is actually can since it has a lot of excess of electron, okay, excess of electron. So this one, antimony, yes, antimony. So SB is antimony. Thank you. Thank you. So each pentavalent atom covalent bond for adjacent. So it will leave one extra. So this one extra, now we are seeing one block. It is actually we have millions of blocks. So millions of free electrons exist. Okay, so this free electrons is actually creating the majority carrier. Okay, so the majority carrier in N-type semiconductor is electrons. Therefore, this will produce a lot of free electrons, and holes are the minority carrier. All right. So this is what happened in other drawing. So we have excess of electron here. Okay, if we dope with many, so we have a lot of excess electrons. So this is how it looks like the crystal structure, like I said just now, the crystalline silicon. Okay, so a conduction electron created by this doping process does not leave a hole in the valence band. Okay, so this doping process lowers the resistance. When lowers the resistance means you can conduct current. Okay. Okay, all right. So yeah, like that. Okay, so okay, so lowers the resistance means, for example, you have I. You have I equals to V over R. Okay, assume that voltage is fixed. So when resistance lower, so you can produce a lot of current. Okay, so for the P type. Okay, P type, the example is boron. Okay, boron. So boron, we known as a acceptor atom because cannot complete the valence band. Cannot complete because it less one atom, okay, to fill out this part. Okay, so for this case, when we see in many blocks, so we can see that the majority carrier here is holes. Okay, majority carrier is holes. Okay, so impurity with 3 valence electron, trivalent. So for example, group 3 is boron, gallium, and indium. So for this case, okay, each trivalent atom forms a covalent bond. Okay, but there is one adjacent with the adjacent silicon, and there is a one hole. Okay, one hole. So if we look at many blocks, so there will be many holes, and this one holes are the majority carrier and electrons are minority carrier in p-type semiconductor. Okay, why we call it as an acceptor atom? It tends to accept other electron to fill up the hole. Okay, so that's why it call it as acceptor. I think you know this. Okay, so let me just recall. So pure semiconductor almost equal number of electron and holes. So n-type semiconductor, when you dope with n-type means you dope with antimony just now. So you will produce a lot of excess electrons. So majority is electrons, minority is carrier. So for the p-type, let's say you dope with boron. So there will be majority carrier holes and minority carrier is electron. All right, so at room temperature, an intrinsic semiconductor has some holes, okay, in it due to what? At room temperature. So when I say room temperature means we put at high temperature. Okay, at 0 Kelvin, no temperature. Now at room temperature means high temperature. Okay, so an intrinsic semiconductor has some holes. Why? Because of when we put at high temperature, the valence band, the valence electron at the valence band tend to jump, okay, to pass through the energy gap and jump to the conduction band and become free electron. So at high temperatures and leave a hole at the valence band. So that's why in intrinsic semiconductor, when we put at high temperature, hole is in it is due to the covalent bond break. And the valence band jump to the conduction band and leave a hole. Okay, so that's how you answer. All right, so the merging of free electron and hole is called what? The merging. The pair of electron and hole we call what?
Electron hole pair.
Rejuvenation.
Electron hole pair. Yes, electron hole pair. Okay, so conduction just now, okay, conduction electron is where the valence electron pass through the conduction band and become free electron. Okay, so the pair is electron hole pair. Okay, so what electrons are responsible for current in material? What electron?
Free electron.
Because of the transferring from the valence bond to the condition one.
Okay, great. So in other words, it is free electron, or what are the other name than the free electron?
Valence.
No?
Conductor.
Conduction electron. Why conduction electron? Because it is at conduction band. Okay? Okay, what are the difference between pentavalent and trivalent? Simple. Okay. Pentavalent has 5 valence electron. Okay. Trivalent has 3 valence electron. Okay. Right. Okay. So what are the process are the majority carrier produce? What are the process? What are the process I'm talking about? To produce to increase the conductivity. What are the process just now?
Doping.
Process.
Yes, doping process. Okay. So doping process is actually dope the pure semiconductor with other element such as p-type or n-type. All right. So number 3, what is the difference between intrinsic and semiconductor? Extrinsic semiconductor. What is simple way? What is intrinsic?
Pure semiconductor.
Pure semiconductor.
Yes, correct. Pure semiconductor. Extrinsic. What is extrinsic?
Semiconductor that can flow the current, conduct current.
Yes. After being a doping process, an extrinsic semiconductor can have better conductivity, can conduct current. Okay. All right. Great. Is that all? Oh, we finished. That's fast. Okay. What time now? All right. Great. Okay. So maybe okay, let me show you. What are you seeing now? What is in your screen right now? Can someone tell me?
Your
Your-
photo, doctor.
Oh, my
desktop.
photo. Oh my God. Okay, let me close it. Oh, okay. Sorry about that. I just closed the slide. I'm thinking about to actually continue a bit, or you want to continue in the next class? A bit. Just a little bit. Introduce about what is diode. Okay. Don't worry. We have not yet entered the fun part. Okay. Why I said fun part is because where we analyze the circuit and so on. Not yet the fun part. Okay. Just the beginning of it, where boring stuff, what PN junction, electrons, so on. But this time, no more. Okay. So I'll go a little bit about 10 minutes and then we finish early. How about that? Okay. Okay.
Okay.
Okay.
It's okay.
All right,
Great.
doctor.
Great. All right. Okay. Okay, so now we go the next part. Okay, so the diode. Okay, diode. Okay, just part 2. Sorry, I think not this one. Oh, part 1. Part 2. Okay, it's raining here in UTM right now. Just reporting to you, all of you. It's not in UTM. All right. Okay. Just 10 minutes, okay? All right. Okay, so we will go through the diode, okay? So for part 1, so diode, we have 3 parts, if I'm not mistaken, now with part 1. Okay, next class also, we still continue this slide, okay? So I have upload both slide. If you see the e-learning, I have upload the lecture 1 and also the lecture 2 for PN junction as well, if I'm not mistaken, okay? So the outline is the PN junction. Okay, you know that when we talk about PN junction, The most famous is diode. Okay, diode is the concept of diode basically. So the characteristic of diode, the operation of diode. So diode operate in forward bias and reverse bias. So you have the idea just now. Okay, and also the IV characteristic and temperature effect. Why temperature effect? Very important. I think you already got the idea just now. Okay, why temperature is effect is important, because temperature is proportional to the conductivity. Okay, when you put that when temperature increase, so the conductivity increase, means you able to produce a lot of free electron movement, and current will increase. Blah blah blah. So this diode, so the junction. So the important is as you can see the LED. Okay, PN junction. So diode is a semiconductor device with a single PN junction. Okay. Okay, so if we draw, so this is your diode. I think I have shown just now. So this is diode. So this is P and N, right? All right. So so diode is constructed as a single piece of semiconductor material. One sided is P-type, the other side is N-type. Okay, so this is how it looks like. What is PN junction? Like I said, it is in between the diode. So this junction. Okay, so this junction is actually, it varies, you know, it can be, the junction can overlap to each other so that this electron can pass through and to the N region, and so this gap is very, very small, or this junction can be very wide. Okay, very wide, and electron cannot pass through, and therefore there is no current flow, okay, in it. Okay, so the region where the two materials join, we call it as a PN junction. Okay, at room temperature, there are large of free electrons. Why I said looks like room temperature is not as a high temperature, but room temperature consider high temperature. So there are large number of free electrons in the conduction band. Okay, like I explained just now. So I think you have the idea. So temperature do affect the movement of free electrons. Okay. Okay, so these free electrons are randomly moving in all directions. So the movement is actually produce a current. So at instant PN junction formation, diffusion takes place. Okay, so due to the difference in concentration, okay, free electron near the N region begin to diffuse to P region. Okay, this is what I said. Okay, so okay, this is what happened in it. Okay, so PN junction forms, okay, when hole from P-type will diffuse into the N-type. Okay, hole here will diffuse, means it move, okay, from P-type to the N-type. Okay, and electron from the N-type will diffuse to the P-type. Okay, why? Because when there is a bias here, okay, so it tends to move. Okay, when at high temperature, so like I said, at 0 Kelvin, no one is moving. So it is unexcited. So it stays at its place. Okay, but when they're at a high temperature, so everyone is moving. Okay, because everyone is get excited by the energy from this temperature. So holes tend to go to the N side, electron tend to go to the P side. So in easy way is to understand that it is attracted to each other. Why? Okay, in some sort of basic knowledge, electron is negatively charged. Okay, electron is negatively charged. Okay, and holes is positively charged. So when positive and negatively charged are different charge, so it tend to be attracted to each other. So this electron here tend to flow to the p-type, and holes tend to flow to the n-type. Okay, so this combination of electron and hole at the junction takes place. Okay, takes place. So when everyone moving around, so at this junction, so this we call it as a p-n junction. So at equilibrium reach, no further diffusion. So at equilibrium means at t equal to 0, no one is moving around. Okay, you will you will stay at its place. Okay, so as electron majority carrier move across the junction, okay, so electron will fall into holes near the junction in the p region. It become minority carrier. Okay, so the n region lose free electron, which leave behind positive charge near the junction, and p region loses hole, and electron and hole will combine, and negatively charged are created and near the junction. Okay, so when I said just now, so when temperature increase, so this hole tend to go to the n region, and this free electron tend to go to the p region. So what happened to this p junction? So this p junction will be depleted. Okay, this takes place, this pn junction. So what happened in here is actually this one. So when this free electron moving around here, move to the p region, okay, so it will leave a hole. Okay, it will leave a hole. So it will leave a hole, and it will create a positively charged near the pn junction. Okay, near the pn junction. However, when electron fill up this hole, since hole is very slow movement, so this electron will fill up this hole, okay, the recombination process. So this hole is actually leaving the negatively charged near the pn junction. Okay, so this region we call it as a depletion region. It is depleted with this deplete with carrier of free electron or holes, but it is filled with charge, positively charged and negatively charged. That's why we call it as a depletion region, where it is filled up with charges. Okay. So this PN junction has potential barrier. Okay, the larger amount of charges, the larger the depletion region will be, the larger the barrier. Okay, the potential barrier. Okay, so barrier is actually the gap. Okay, the gap. Okay, the gap, not energy gap, but this is actually in terms of voltage. Okay, voltage barrier. Okay, so voltage, the very potential difference is the potential between the PN junction across the depletion region. Okay, so this is the explanation that I explained just now. You can read yourself. Okay, so depleted of charges means no free electron, like I said. So this electron, let me repeat again. So this free electron tend to attracted to the p region. Okay, so when it is attracted to the p region, it will leave a hole here. Means it will leave a positively charged, and this electron who leave the positively charged will fill in this hole. Okay, when this hole is filled up, okay, it will become negatively charged. Okay, this is how it goes. Okay, and this negatively charged will be attracted at the PN junction. Okay, so this positively charged and negatively charged will be attracted to each other. Okay, that's why the depleted of charge carrier means no free electrons, no holes, but only charges. Okay. Okay, so depletion region is formed very quickly, and it is very thin. Although the drawing looks like very wide, but it is very thin. Okay, compared to the N region and P region. All right, so now we are talking about at initial state. Okay, at high temperature, unexcited. When we put high temperature, so this movement of free electron will become excited and will fill up the holes and so on. Okay, with no biasing, no bias yet. Okay, no bias means no voltage, no battery, no voltage applied. Only temperature. Okay, only temperature. So what happened when we apply bias to the PN junction? Or for example, we apply bias battery to our diode. Okay, what happens? Okay, this is what happened. Okay, so so this is your PN junction. Okay, so this is your PN junction. So this is no bias. Okay, so what happened when we apply positive, okay, to the P side? Okay, so this is P side. This is N type. Okay, N region, P region. So what happened when we apply positive to the P type and negative to the N type? Okay, what happened here? Okay, let's take a look. So for no external voltage apply, okay, for no external voltage apply, VD, voltage drop is 0, no current flow, and only modest depletion layer exists. Okay. Okay, no voltage source means no current flow. But there is a depletion region created, but no, what can I say? This diode is not yet forward bias. Okay, not yet. Okay. So with the application of DC voltage means we apply battery to the diode or to the LED, for example. Okay, obtain desired mode of operation. So the polarity of the connection will play a role now. Okay. So there are two types. Okay, you can make your PN junction become forward bias, or you can make your PN junction become reverse bias. But how you make it become forward bias and reverse bias? So for this case is diode is on. For this case, you make your diode off. Okay, so how you decide your diode, how you decide you want to turn on your diode or turn off your diode is how you plug in your voltage. Okay, make sure that you plug in your voltage correctly. Okay, correctly. Okay, so the applied potential causes the N-type material to be negatively and P-type to be positively. All right. So let me show how. Okay, so for forward bias, make sure that your diode is connected to positive terminal to the P type and N type to the negative terminal. Okay, for the if you want to make your diode off, no current flow. Okay, make sure you connect it to the alternate negative to the P type, positive to the N type. Okay, so this is how you make your diode become forward bias or reverse bias. Okay, for example, this one. Okay, so this is your diode. Why we put resistor? So I think you have learned in the electrical circuit analysis. So we put resistor is to control amount of current. Okay, we cannot like if we have no resistor here, so current will be directly connected to the diode and it may destroy the diode. Okay, but we put resistor because we want to limit the current. Okay, to tone down the current, so that why we put resistor as a complete circuit. Okay, so this one, positive bias connected to the P type, negative bias connected to N type. So this will become forward bias. Okay, so what happened here? What happened? Okay, so when we apply this, so what happened to the PN junction? Okay, what happened to this PN junction?
Forward bias.
Yes, it will become forward
Forward.
bias. So this PN junction will become narrower. Okay, it will become narrower, means become thin. Okay, so this barrier, okay, so this barrier is actually low barrier. Okay, why low barrier? Meaning that, okay, why is this happen? Okay, let's see here. Okay, so these electrons, okay, move. So this electron, so this is positively charged, so this is negatively charged. Okay, let me draw it again. Okay, so in P type, you know that many holes. Okay, in N type, you know that many electrons. So when this plate is positively charged and this plate negatively charged, okay, so this is the voltage. This is the voltage. Okay, when we increase the voltage, okay, so when we increase the voltage, So what happens? So this is positively charged. We know that the electrons, okay, the free electron is negatively charged. The behavior, the nature is negatively charged. So therefore, this negatively charged will be attracted to the positive plate here. Okay, it has attraction. Okay, because the voltage is very high for the positive. So free electron, which is negatively charged, will be attracted to the positively charged. Okay, what happened to this hole? Holes as well as hole will, since it is positively charged, it will be attracted to the negatively charged. What happened to this PN junction? Since it is movement of attraction between positively plate and negatively charged, so this PN junction, okay, so the barrier will become lower. Okay, so the barrier will become lower. So this will become very, very thin barrier, almost overlap maybe. Okay, almost overlap. So electron can pass through. Electron can pass through. So there are moving of electron. Then only you can measure the current. Okay, so since there is very small barrier, okay, meaning that everyone can pass through, okay, can pass through the barrier, the hole can pass through the barrier, the electron can pass through the barrier, and this is become very, very small, okay, no barrier, and this will become forward bias. Okay, forward bias means electron can pass through and you can measure the current. Okay, so this is how it looks like. Okay, so the resistivity here will become very, very small. Okay, then current can pass through. So this is what happens in forward bias diode. Okay, so more how blah blah blah. So depletion region, the key is depletion region, or the barrier will become narrower. Okay, the barrier will become less, and when no barrier, no almost less barrier, so this is very easy everyone to pass through, and current flowing in this forward bias diode. Okay. Okay, so this is the animation. Okay, how it goes actually. So as you can see, the depletion region become narrower, and voltage barrier here, voltage drop here is very, very small. Okay, so therefore you can measure the current. Okay, in this case, the effect is depletion region narrower and electric field barrier reduced. Electric field means the voltage barrier. Say what happened reverse bias? Okay, reverse bias, you apply vice versa. Okay, you apply vice versa. Just now you apply positive plate, okay, to the P type, negative plate to the N type. Now it is vice versa, where you apply negative plate to the P type, positive plate to the N type. Okay. All right. So what happened? So since this is many holes, okay, and this is free electron. Okay, and this is negatively, and this is positive. All right, so just now it is attracted to positively. Now holes is attracted to this negative. Free electron is attracted to this positive. So when we have larger voltage, okay, larger voltage, so this free electron and hole will take place in attracted to this terminal. This one also attracted to this terminal. What happened in the depletion region? So no one is so cannot pass through the barrier. So this depletion region will become wider and barrier become increases. Okay, barrier become increases. When this barrier become increases, so no one can pass through this. Therefore, this will be open. It's like open. Okay, it's like open. So it won't allow current to pass through because electron are moving to the plate, to the positive terminal, and they want this one to the negative terminal. So no one can pass through this barrier. No one. Free electron or holes, no one can pass through. Therefore, this one will become open circuit, or we call it as a reverse bias. Okay, and for this case, for this case is current Okay, current is equal to 0. So this one is reverse bias and electrons cannot moving around because of this large barrier, and current cannot be produced. It is equal to 0. All right, so this is what happened if we look at the, there is current, but extremely small and approximately equal to 0. And this is due to the reverse bias. Okay, I hope up to now you're already clear what is forward bias diode and what is reverse bias diode. So how we do, what happened to the depletion region, and what happened to the barrier. All right, so when we talk about depletion region is at the PN junction. So there, when depletion region increase, the barrier increase. When depletion region decrease, so barrier will be decreased and current will start flowing. So I hope until up to now you can differentiate between forward bias diode and reverse bias diode. Right, so I think that's all for today. Okay, we will continue the lecture on Wednesday. Hello? Hi, everyone.
Yes.
Yes.
All right,
Thank you.
great. All right,
Okay.
great. Okay,
Later.
thank you for staying with me throughout the lecture. If you have
Thank
any
you, Doctor.
question, you may ask in the group. Okay. I think that's all for today. We will continue our lecture on Wednesday. Okay. For those, I think for those who can't, who didn't slide yet, you want the attendance again, or everyone has scanned the attendance? Done. If not, I can show it again. I think everyone is done. All right. Okay. Thank you, everyone. If you have question, you may ask in the group. See you on Wednesday.
Thank you, Doctor.
Okay.
Madam.
Okay. All right.
Thank you,
Great.
Doctor.
Okay. Take care, everyone. I hope to
Thank
see
you,
you on
Doctor.
Wednesday. All right. Okay. Stay safe, everybody.
Doctor,
Yes. Yes.
I wanted to ask you about the old and the new code. So, what do you think I should do? Because I already like there's a form from the office. I already fill it and I send it to them through the Google form. And I just like I want to make sure that all the thing will goes all right. Because in my handbook, the code of the subject is SKEE, and now it's EE.
Okay, okay. So, Muhammad Mantar, so I think I need to ask the academic manager, and then can you PM me first in the Telegram so that I can reply you after I ask the academic manager?
Okay, Doctor, inshallah.
All right.
So,
Okay.
all right.
All right. Okay. Okay. All right. Take care. I
Thank you very
will
much, Doctor.
reply
Thank
you
you.
later. Okay.
Assalamu alaikum.
Welcome. Waalaikumsalam.